Hello children, welcome back to the channel. Today we will be continuing our discussion on gravitational potential energy. If you remember in the last class what we have found is that gravitational potential energy at a given point of the gravitational field of a given mass capital M at a distance of r from the center of the given mass for a body of mass small m was given by minus this expression minus gmm by small r. M being the mass of the body, massive body, whose field the smaller mass m is placed at a distance of r. The center to center distance of the two masses is r. Okay. Then we said that we will discuss certain aspects of this particular expression. Let us say what we observe from this expression, gravitational potential energy, if it is given by this particular expression, what do we observe from this? First and foremost, what we see that it is always a negative term. Gravitational potential energy is negative, right? Number one, it is always negative. So what it means is that gravitational force is an attractive force, as we know already, right? And so the work is done by the gravitational field, not on the gravitational field. Now, when we say it is always negative, means that when we move from say infinity and we move closer and closer to the object, what will happen? The value of r will decrease, right? Initially it was infinity, then it comes to a smaller and smaller value, and as we come closer to the body, what will happen? If the value of r decreases, the term gmm by r, its value will increase, right? If the value of this term gmm by r increases, so what will happen is that because of the negative sign, the entire value of the right hand side will keep on decreasing. The magnitude of the negative value increases means that it becomes more negative, or the value or the entire term becomes more negative, and so its value decreases. Which means that number two, that if r increases, conversely, say this is the center of the mass m and this is say r, the object is at this distance r. As we take it further and further away, as r increases, what will happen? This term will increase. If this term increases, this fraction will decrease. If this fraction decreases, the negative term, because of the negative term, the value will be less negative, which means as r increases, u increases. It will always be negative, but as we move away from the center of the mass, whose in the field of which we have put the test mass, that is whose potential energy is being measured, if we take the small mass, that is the small m part, away, or if the distance between the two masses keeps on increasing, the magnitude of the negative value will decrease, which means that the value will increase, which means that maximum value of u will be achieved at an infinite distance, at infinity, and u maximum value will be 0. So at infinity, the gravitational potential energy was 0, and then it kept on decreasing as we move closer and closer to the given mass. Okay. Now, in such case, if we say initially the mass was at r1 and then we took it to some other point, say r2, the small mass m. If small mass m was at r1 and then we took it to r2, so initially the gravitational potential energy was minus g m by r1, and the final potential energy will be minus gmm by r2, right? which will mean that U2 minus U1, that is change in potential energy, will be this term minus this term, right? U2 minus U1, which means minus GMM by R2 minus and minus plus GMM by R1. So if I take GMM common, then we have GMM by R1, so we multiply by 1 by R1 minus 1 by R2. So if I take the object from R1 to R2, the gravitational potential energy will change like this. If R1 is greater than R2, then delta U is negative. Right? Why? Because this term being greater than this fraction will be smaller compared with this fraction. Thereby, the whole term will be negative, so delta U will be negative. Conversely, R1 less than R2 will give us delta U positive. Right? Like this case, R1 was closer, R2 was further, so R2 minus R1, this will be a positive term. Okay. So, if we bring the bodies closer together, the gravitational potential energy will decrease. If initially the object was there and it came to this particular point, then gravitational potential energy will decrease. Okay, now if we note this particular case, and let us consider the case of Earth. That let's say this is the Earth, this being the radius, right? And m is the mass of the Earth. And let's say this radius, initially the object was here, R1 is equal to the radius of Earth, that is the mass was initially here, small mass m. And finally we took it to a particular height above Earth's surface. This height, let's say, is h. So when the mass comes here, the total distance from the center of the Earth will be r plus h. Let's call this r2. So initially the object was at r1 and it is at r2 from the Earth's surface. So initially the object was on the surface of the Earth, and then we take it to this height r2. Then what we have? Substitute the values here. We have GMM. R1 is 1 by R minus, this is 1 by R plus H from here. So if we take 1 by R or common also, GMM by R, what we are left with 1 minus R by R plus H. Fine? Are you with me till now? So, in this fraction, right, what we can do is that we can rewrite this as GMM by R is there, 1 is there, minus, instead of writing it here, if I divide both numerator and denominator by R, what we have? 1 by 1 plus H by R. Right? So what we can do is that we can rewrite this expression right hand side as, say, delta U equal to G capital M small m by R is there, 1 is there, minus 1 plus H by R inverse raised to the power minus 1. This term is 1 plus H by R raised to the power minus 1. So if we assume that this H is much less compared with R, so the height above the Earth's surface that we have taken the mass to is small, very negligibly small compared with the total height of the Earth's surface, total radius of the Earth. Then we can say this fraction inside the bracket H by R is negligibly small, and so we are able to expand it binomially and then we will have discard the higher order terms. So what we have, Gm small m by r, 1 minus, this will be 1 minus h by r, and the higher order terms can be discarded. Once we do this, simplify this, ones will cancel out, minus minus will become plus, so we have Gmm r into r, that will be r square into h. However, this part Gm by r square is the acceleration due to gravity on the Earth's surface, right? So, change in potential energy when we take the mass from the surface of the Earth to a height h, which is small compared with the total radius of the Earth or the radius of the Earth, then we have this equal to small m is there, this term will be replaced by g and h. So, what we have seen is that we have arrived at the expression that we have been using for potential energy from the very beginning. That potential energy above the Earth's surface, if we take the object from Earth's surface to a particular height, its potential energy becomes mgh, which is actually the change in potential energy we are talking about. And we have also mentioned that potential energy is something which we take the zero level is arbitrary. So we say that due to Earth's potential energy, on the surface the potential energy is zero, at a particular height the potential energy is mgh. What actually we have meant is that the change of potential energy when we take the object from the surface to the height becomes mgh. Okay, so we have discussed about gravitational potential energy and found an expression for it, and we have also discussed how it varies with distance, that it is a negative term and everything. Now, what if instead of m, this test mass or the mass whose potential energy we have taken a unit mass? That is to say, what if we divide this expression by m? We have already discussed that this gravitational potential energy at a given point is nothing but the work done in bringing in a mass from infinity to that particular point. So this is nothing but the work done. Okay. So if I divide it by m, this whole expression, that is to say w by m, which is u by m, or which is equal to g m by r minus of gm by r. This term is nothing but work done per unit mass, right? So this term is known as the gravitational potential of at that particular point. Which particular point? At a point which is at a distance of r from the center of the massive object in which gravitational field we have put the unit mass. So this is work done per unit mass. So gravitational potential by definition is, it can be defined two ways. Number one is that it is the work done in bringing a unit mass from infinity to that particular point in the gravitational field. As the potential energy was the work done in bringing the mass m from infinity to that particular point, gravitational potential is similar, but it is, in this case, instead of the mass we have a unit mass. The test mass's value is unity or 1, not m. So if I take a unit mass and bring it from infinity to that particular point without any acceleration in the gravitational field, then that particular work done, which is given by this expression, will be the gravitational potential at that particular point. In other words, we can also say that it is nothing but the potential energy of a unit mass placed at that particular point. We said that if we have a gravitational field and this is a distance r, this is a point P, mass m, and if we place a mass small m here, then its gravitational potential energy was gmm by r. Here, instead of small m, if I put a unit mass, that is 1 kg or 1 gram, depending on the scale we have taken, then if I put a 1 kg mass, whatever potential energy it will have will be called the gravitational potential. So gravitational potential is nothing but work done per unit mass or potential energy of a unit mass placed at that particular point. Okay. So since it is work done per unit mass, so its unit will be joule per kg or erg per kg, and its dimension of gravitational potential will simply be dimension of work m L square T inverse 2 divided by dimension of mass, that is m. So it will be m0 L square T inverse 2. Okay. So from this expression we can say clearly that W, which is nothing but potential energy of a mass m, is simply V into m. Right. So if we know the gravitational potential at a given point, we can find the potential energy of any given mass. Whatever value of m we take, we simply have to multiply the gravitational potential V by the magnitude of the mass. And that is why it is useful to define gravitational potential, although we already know the gravitational potential energy for a given mass m. So if I place different masses m1, m2, m3 different at a particular point P in this gravitational field, given gravitational field, what will be their potential energy? We do not need to calculate them separately one by one. If we have first calculated the gravitational potential energy, then we simply multiply the gravitational potential by the magnitude of the mass m1, m2, m3, and we get the gravitational potential energy. And that is why it is important to know or find gravitational potential. Okay, now let us consider a planet of mass m and radius r. Now, from our experience, let's consider this planet's art for the time being. So what happens that we know that if we throw something upwards, it always comes back, right? You throw with a lesser amount of force, it goes to a lesser height and then comes back. You apply more force, it goes to a particular height, but it still comes back. Why it comes back? Because it is not able to go beyond the Earth's gravitational field. It is not able to escape the Earth's gravitational field. What if we apply such a high velocity, initial velocity, that it escapes, the particle escapes the Earth's gravitational field? What do you mean by escaping a gravitational field? Is that we mean that it goes so far away that the effect of the field is no longer felt, or the field can no longer exert sizable amount of force on or measurable amount of force on that particular particle. We know that gravitational field has an infinite range, so to escape the gravitational field, it has to go to infinity. So with what speed we should project a mass m, say, and say speed of VE, so that the object escapes the gravitational field of the particular planet. So this is quite opposite to what we have been discussing till now. What we did initially prior to this is that how much work needs to be done or is done when we bring an object from infinity to a given point within the gravitational field. Now what we are saying is that the object is inside the gravitational field, is on the surface of the planet. We want to do or give some amount of energy to it so that it is able to overcome the Earth's field and go to infinity. So what we assume is that, let us consider first, to find this, let us first consider the point P, which is at a distance of x from the center of the planet. Okay, so at this point there will be a gravitational force of attraction which will be given by g m small m by x squared, right? So if I have to take the object from P to Q, where Q is at x plus dx, so distance between P and Q is so small that the force of gravitational attraction can be considered to be constant for both, same for both P and Q. Under such conditions, what will be the work done when we bring the object from P to Q? will simply be f into dx. Okay, we are talking the magnitude here, or which will be equal to g m small m by x squared dx. Okay. So what is our objective? Our objective is to take the object from here, from the surface of the earth to here, that is infinity. We know taking it through a distance of dx from P to Q, this much work needs to be done. So the total work done in taking the object from earth surface to infinity will simply be W will be integration of dW with proper limits, and the proper limits will be from the earth surface to infinite distance g m by x squared dx. Solving this will give us g m, these are constants, minus 1 by x integration 1 by x dx infinity, sorry, r to infinity. Substitute the values. In 1 by infinity will be 0, and then minus 1 by r, so this will be a positive term. So work that needs to be done will be positive, and that will be gm m by r. So we need to do this much work for the object to escape. Now how do we do this much work? By providing it with an initial kinetic energy, by virtue of its initial projection velocity, the velocity with which we project the object. So what is the kinetic energy of projection? It is half m v e squared, right? So this velocity will be escape velocity. This velocity will be able to impart sufficient amount of kinetic energy for the object to escape the gravitational field, if and only if this is equal to or greater than the work that needs to be done to take the object from here to infinity. Now we are considering the minimum velocity required. So what we are saying that this kinetic energy must be equal to, at least equal to the work done, or should be able to do this much of work, which means these two must be at least equal. If we equate these two, we get half m v escape squared is equal to g m by r. M's will cancel, and so we have v escape velocity with which an object needs to be projected so that it escapes the gravitational field of the given planet, will be 2gm by r, and square root of this term. Okay, or we can rewrite this as 2, we know that g equal to gm by r square. So gr will be equal to gm by r. So gm by r can be substituted with g into r. That is another expression for it. And also, if we try to express it in terms of average density of Earth or of the planet and the radius, then m will be equal to 4 by 3 pi r cube into rho. So if I substitute that value here, 4 by 3 pi r cube, and r is in the denominator, so we can rewrite this as, instead of 4 it will be 8, right? 2 into 4, that is 8 pi g pi rho g r square divided by 3. You substitute the value of m by this, you will get to this expression. Okay. Now, if the planet were Earth, we have considered any given planet. If we say the planet is Earth, then this particular expression, what we have, G we know is 9.8 meter per second square, and the radius of Earth is 6,400 kilometers roughly, right? So we can say that 6.4 into 10 to the power 6 meter. If you substitute the values here and then solve the problem, we will get escape velocity from Earth's surface is almost equal to 11.2 kilometer per second.